This video has been supported by PCBWay. Hey guys, happy World Metrology Day! Today I'll attempt to build this programmable Nanovolt switch to automate various inter-instrument connections and basically to give my new baby here many new inputs to play with. Enjoy! If you remember, last year I built a lot of these 10-volt DC standards for testing and calibrating voltmeters, for testing and calibrating ADI's brand new Xena reference, and for testing your patience in a painstakingly detailed hour-long video that I made back then. The results look promising. My voltmeters are able to measure voltages, ADR 1000 is a pretty good Xena reference, and the attention span of a YouTube audience can be stretched far through unpredictable plot twists. No, seriously, I've published the first year results in the ADR-mu GitHub repo. And while we are not consistently surpassing the datasheet specs of a $10,000 fluke standard, I am happy with them so far. What I'm not happy about, and that's the point of this long-winded intro, is the method with which I've taken these periodic measurements until now. I used a relay scanner card to connect the voltage standards one by one to the 3458As, which then take direct 10-volt measurements. For every day, I calculated the average of the best 4 or 5 boxes. And then what I was actually recording to judge stability of all participants is the difference between an individual voltage and the average of the most stable reference group. By looking only at these math differences, I had hoped to lower the voltmeter's error contribution in my results. And that worked. Had I analyzed direct voltmeter readings instead, the results would look worse. To be fair, I did experiment with some new cooling options for the 3458s, so these large jumps are not natural. But they are present in everybody's data, so it cancels itself out and doesn't matter. Well, except, fundamentally, we are still relying on a multimeter's 10-volt range, with all the associated noise, tempo and uncertainty. The effect of that is that even though we are seeing less than 10 microvolt drift over a whole year, we are rarely getting less than 2 or 3 microvolt from one day to the next. Everything could be so much better if instead of taking 10-volt measurements for a mathematical subtraction, we made milli or microvolt measurements in the appropriate range after an electrical subtraction. And that is something that the United States National Bureau of Standards Technical Note 430 from 1967 specifies. Oh yeah, we sure are at the bleeding edge of technology here at the Reps Labs. By connecting two references in series opposition like this, we can measure their voltage difference directly between their positive terminals in a lower voltmeter range, at much better resolution and all the other improved specs. And there is another free advantage on top. If somebody used this with inferior products without pure copper terminals or cables, they would ordinarily get a well-deserved slap on the wrist in the shape of a small thermal EMF error. However, if we could just reverse the series opposition connection, while leaving the test setup unchanged, we would get an inverted representation of our voltage difference, with which we could cancel out all static thermal EMFs. And that, at long last, are some of the requirements of whatever I'm going to build today. So what options are there for connecting things in series, for flipping them around and connecting them to a voltmeter? Well, I could always sit down and handwire these connections, of course. I would estimate around 5 minutes of work per ADR-mu pair per day. Uh-oh, that sounds like an exponentially growing problem though. In my present set of 9 boxes, there are only 36 unique combinations, or 3 hours of work. But if I ever made it to 25 DUTs, there wouldn't be enough hours in a day to work through all the permutations. So it'll have to be something that can be automated. Relays come to mind naturally in any automatic signal routing context. And sure enough, there are very, very good relays out there. The best voltmeters and calibrators use them. Since we are planning to deal with very low voltages, we have to be careful though. Relay manufacturers care first and foremost about their usual datasheet specs, cycle life and ampacity, that sort of thing. There's no money to be earned with nanovolt accuracy, so they usually coat their non-copper contacts with exotic metals to make them live longer. And to make them nice and compact, the coils tend to be very close to those contacts, causing wonderfully uneven heating of those dissimilar metals and therefore lots and lots of thermal EMF. Even these special, custom, $10 low thermal EMF latching types, even a minute after having pulsed the coil, are not that good, unfortunately. Yep, that's hundreds of nanovolt coming out of this short circuit for multiple minutes after actuation. Yay, free energy discovered at last. Ultimately, this specimen will settle down to around 60 nanovolt, which isn't entirely hopeless. And there are better latching relays that, when flipped with the absolute minimal impulse energy, would work quite well for me. But there are a few more options to consider. Keithley used to make this Nanovolt scanner card, where they basically built solid-state relays out of JFETs and batteries. Now the JFETs have tinned copper legs and gold bond wires and a silicon die. So they will certainly generate some offset voltages, but when used correctly there are equal numbers of thermally matched JFETs on the plus and minus sides of a signal. So differentially Keithley can guarantee less than 30 nanovolt offsets, making this a tempting option for me too. There is a small catch, and that's the on-resistance of these JFETs. I'm hoping to use my creation for some resistance metrology later, and therefore I'd like to avoid any kind of systemic resistance. Commercially there are not many good options, and those that are available cost many $1,000s. The data-proof scanner is the only one I've ever seen for sale on the second-hand market myself. Internally, this one relies on a special type of relay called Printect. Basically, it's just the electromagnet, armature, and contacts of a latching relay, but mounted in such a way that it can make contact or not with PCB traces. So these are maintenance friendly, and a user can choose at least one side of the contact plating. But nowadays, I'm afraid Printect relays are all but extinct. And if a whole data-proof scanner ever showed its face on eBay again, I have no doubt the VoltNut community would mobilize their entire retirement fund and bid that into oblivion. Hey, I would do the same. A paper by the
Bureau International des Poids et Mesures.
Bureau International des Poids et Mesures is proposing a low thermal EMF scanner built from rotary switches, which are then operated by stepper motors to make and break the connections. They say only that their rotary switches are custom products based on the C4 series by Electroswitch Corporation. Whether or not they ordered special copper wafers with no plating, or just more pins, I'm not sure, but their results showing few nanovolt repeatability instantly made me fall in love with this idea. Here is one such Electroswitch C4 with the lowest pin count, and therefore the lowest price at the usual distributors. Still $40, that's hefty. I think this standard model uses silver-plated brass for everything. Seems okay EMF-wise. As long as the silver isn't worn off and there aren't any large thermal gradients in the switch. It is very, very sensitive to thermal disturbances. If the finished product is ever placed on a warm multimeter or something accidentally, I bet it'll put out wrong readings for an hour or two. I did have a larger scanner in mind with some flexibility for different purposes, so I don't like the at least €40 price tag for these. My final exhibit for today had a much more wholesome price. This gorgeous pure copper pin, pure copper wiper rotary switch has been given to me as a souvenir. Unbelievable. The self-cleaning, lubricant wicking laminated wiper, the thermal insulation of the knob, and the instant settling down to single-digit nanovolts that this artifact is capable of are just sexy. I didn't even have to oil it up in deoxit for that effect. A huge thank you again to the donor, and this is obviously not meant as a complaint, unless it results in more of these switches. But out of just one, I can unfortunately not build the most epic nanovolt multiplexer ever. This one was a great source of inspiration though, and after mixing it with a few of the other options, I think I can see a plan beginning to take shape. At the risk of reinventing the wheel once more, I will try to make my own nanovolt-capable motorized rotary switches. Most importantly, I want this to be cheaper than one Electroswitch C4 per axis. Otherwise, I could just use an Electroswitch C4 per axis and spare myself all the mechanical troubles. Secondly, I want large, pure copper features for temperature independence and maybe even sub-milliohm contact resistances. I'm kind of borrowing these slanted pads from my pure copper artifact, hoping that they will help the wiper to glide over them without extra abrasion, without getting too close to any historically burdened symbols. The only solder connections that will be allowed on here are for a kind of limit homing switch. All the mission critical stuff will of course be bolted down copper ring terminals. Ew, gold. No thanks, bro. Practically, a gold plating, even with an in-between nickel diffusion barrier, makes little difference. But like, this would wear off soon, so we might as well commit fully to the shiny copper theme. Huh? Why isn't it accepting orange? Oh, but red is okay, huh? Nice copper discrimination. Let's hand this over to the copper experts at PCBWay. The BIPM paper, the guys with the electroswitch C4, mentions anchoring of all the connections on a thick, thermally conductive metal plate. That way, equal temperatures are imposed on all the metal transitions. And all the signals receive the same thermal EMFs, so they cancel themselves out. Some extra metal also adds thermal mass to a system, giving it a large time constant that smooths over its response to ambient temperature changes. Sounds good. So I'm going to go with a metal substrate PCB, which is going to do the same for all my ring terminal connection points. As well as, and this is something that would not easily be possible with off-the-shelf rotary switches, for all the switch contacts. My mouse pointer seems strangely attracted by the copper core PCB button. But I think we already have a huge advantage by choosing surface finish none, plain copper. So I'm going to try and save some money with aluminium core PCBs, which cost around $2.70 plus shipping per piece at PCBWay. While they take care of that, we have a moment to prepare the mechanical side of things. And this is by far the most time-consuming part of this whole quest. Anecdotally, copper-copper contacts are bad, right? They are prone to oxidation and galling and are easily damaged by arcing if the lore is to be believed. Otherwise, I guess relay manufacturers wouldn't consider such far-fetched contact plating options like ruthenium, rhodium, or tungsten. I can't find a lot of reliable info about this in the context of super low voltage, super low current applications such as mine. It might just be fine, but even if it isn't, a switch wafer costs $3 and the wiper could be a 3D printed part with a piece of copper tape, costing a single-digit number of cents in materials. If one of these would have to be swapped annually, it would still be a pretty attractive package when compared to the many $1,000 commercial product. Making the wiper reliable was tricky and is kind of still ongoing. All copper surfaces in an oxygen-rich environment oxidize, very slowly normally, but it matters in the realm of the nanovolts. We can use inert metal plating, wetting currents in the order of 10 mA, abrasion, or chemicals to counteract that. A permanent film of a gentle contact cleaner such as deoxit, which is rumored to be a descendant of olive oil, by the way, look it up, seems to work most of the time, but it can also cause a form of aquaplaning if the wiper isn't pressed down sufficiently. I want to use a blade-style flexure to maintain gentle but constant downwards pressure, and a living hinge flexure to let the wiper follow contours in spite of deflection of the previous joint. CNC machining these would of course be the right thing to do, but then they no longer cost a single-digit number of cents. And if I made them from metal, they would provide great coupling between my sensitive measurement signals and whatever dirty power is going to run through the veins of my stepper motors. I will exhaust my 3D printing capabilities before considering that. Torsional stiffness also matters for reasons that will become apparent in a moment. 3 single-wall flexure blades in 0.45 mm thickness, printed on the side in ASA material, feel just about right. And ASA has already proven its low creep properties by relentlessly supporting my solar panels through multiple scorching hot summers. I wish Prusa Slicer had an option to allow deeper anchoring of these single-wall protrusions. As is, it tends to create a weak point. By simply starting and ending these single lines near the outer perimeters of the connecting bodies. We are not putting a lot of force on these, so it's going to be okay this time. Resin printing seemed like a great option for these, because it allows printing even thinner walls, and their final brittleness or stiffness can be controlled precisely in post-processing. Unfortunately, the standard resin, the only type I had on hand, turns out to be very creepy. Well, maybe most are, but this stuff especially tends to undergo plastic deformation under strain. That would leave the wipers flaccid in a few days. I did experiment briefly with laser-cut leaf springs which could be inserted into the resin-printed wipers. These worked reliably in a multi-day continuous test. But just like CNC machining, this would undermine my minimalist low-cost concept. So I think I'll stick with FDM for now and hope that I won't discover some super slow creep property there. How naive am I for thinking that I can defeat this high-tech problem with a few millimeters of copper sticky tape? Yes. But now I've grunted into the microphone about it for 15 minutes, so there's no going back anymore. For me in real time it's been a little bit more than 15 minutes, not much. And so my PCBWay package has arrived. I couldn't help myself, I took a little peek inside already. And I ran tens of thousands of cycles in a prototype switch before even starting this video. Wouldn't want to go through all of these preparations just to run into an unforeseeable failure in the end. I didn't, so let's see the coppery beauties that our sponsor has sent over. This is their basic 1 watt per meter Kelvin thermal conductivity option, with a 1 ounce copper layer over a dielectric that almost looks ceramic-y. If a lot of power has to be dissipated by components, PCBWay also offers up to 3 watt per meter Kelvin options. With a properly heat-sunk substrate, this would allow transport of kilowatts of power at a negligible temperature rise. Sounds crazy putting that into words. We'll have to try that one day. In this use case we are only generating little heat in the motors, and that isn't sunk into the switch wafers obviously. So I would guesstimate that even an FR4 board with bare copper features would work great here. My PCBWay contact has once again shown great wisdom in suggesting that I should let them coat the drill hole walls in some isolator. They offer that to keep metallic mounting hardware from shorting out PCB traces to the metal substrate. I refused this time because I already had the nylon screws for the task. But yeah, great advice as always. Currently, in cooperation with the KeyCat project, PCBWay is organizing an open source hardware design contest, where you can submit your awesome projects to win cash prizes or Raspberry Pis. Check it out, link below. I'll leave you all a chance at winning by not submitting my Nanovolt scanner. For motors I would have preferred something cheap like this. We don't need torque or speed or accuracy after all. Alas, these took a month longer than advertised to get here. And you know, with my tight YouTube video uploading schedule I couldn't wait for that. So I ended up using these stubby NEMA 17s which are 5 times as expensive, with no technical advantages, so if you build one of these too, use whatever. Even RC servos might work. Although those usually have carbon potentiometers internally, which might not last long. Does anybody remember anything about a blue brushless No. Let's just forget all about that. Too much cringe. The stepper drivers are also kind of not critical. We are not doing anything difficult, so almost everything will work. I was a bit worried about needing 12 sets of step, direction, enable, and home limit switch GPIO pins, which conventional stepper drivers need. So I chose TMC2209 drivers, which can be completely controlled and read over one exclusive UART pair per driver. I'm using a simple screw and the built-in sensorless stall detection to find the home positions of the wipers. Getting this detected reliably is what the torsion stiffness is for. And I'm using constant velocity movements and time delays to send them to their destinations. Wouldn't recommend in hindsight. It would have been much easier and much less buggy to simply wire all step, direction and home pins in parallel, and then to selectively enable one stepper driver at a time with an exclusive enable pin per axis. I don't know, maybe I'll switch to that later. For now the TMC2209 scheme works perfectly too. It better after all the time I spent ironing out the quirks. I'm going to try and squeeze this thing into a low-cost eBay desktop enclosure. And that of course needs a fitting low-cost 3D printed front panel. A low-cost front panel which is then populated with $200 worth of pure copper banana jacks. Oh, so pretty. I wouldn't make a good criminal. If I ever managed to steal lots of copper, I could never bring myself to sell it. And anyway, the biggest addiction I could sustain through selling would just be more copper, so that would be pointless. This many switchies are of course giving me a lot of freedom regarding their electrical composition. I think I'll go for something like this for now. It lets me combine all combinations of 10 DCV standards, including their reverse polarities, and or direct measurements of up to 5 4-wire resistance standards. Then I would just dedicate this side to the voltage measurements and the others to the current routing. But there is not enough room for a real resistance bridge circuit. That could be done with a whole second scanner. Kinda crazy thinking about how complex this thing already is. I just had this crazy idea while tediously point-to-point wiring my 12 stepper drivers. Why don't we just coat some isolator plate in metal and then etch a pattern into that? Forming hundreds of wires at once. Might even be a lucrative business model, and if not, we just hire some YouTubers to promote it. The switch stuff would also benefit from just being a single plate with all the wires baked in. Having this all reconfigurable for different purposes is nice, of course. But it's literally hours of work to assemble half of this insanity. And then modeling it in software and flipping through all possible input combinations is also not exactly trivial. The payoff, however, is all the sweeter because, who would have thought, this really works as intended. With a few little footnotes. This is massively sped up for illustration purposes, by the way. When taking measurements for real, the motors can move much slower, and the voltmeter will have much more time to ponder the readings. I did also choose a limit switch and step direction control scheme this time, over TMC 2209 software control. Because it turns out that even the gentle bumping of the wiper into the end stop that is necessary for sensorless stall detection weakens the wiper over many hundreds of cycles. Because I didn't fine trim my 10 volt sources to 10.000000 volt, there are sometimes many millivolt between them. That may seem a bit awkward after I've put so much effort into the well-being of nanovolts. But believe me, there will be many nanovolt critical use cases if this turns out to be as reliable as it is beginning to look right now. I have here about the week of runtime with thousands of switching operations and a few interruptions for last-minute changes. This may already be enough cycles for about a year of runtime, if each combination is only tested once per day. Love to see my previous 80 RMU specs confirmed to some degree. The yellow trace, for example, corresponds to the difference between boxes 6 and 11, my Tempco champions. And indeed, over the course of multiple days, and throughout various ambient temperatures, they agree with each other, within 0.2 ppm. Previously, this would have been invisible within the measurement noise floor. I also logged a short circuit made with 2 scanner switch contacts. Here we are getting tens of nanovolt consistently, which is probably mostly meter Tempco. If so, this could be eliminated by using the meter's null function periodically. Some wear debris is visible on the wafers that have gone through all these cycles. But they are nowhere near worn out yet, so there might be multiple years of use in a set. Pure guesstimation at this point. With a nulled meter test lead, the resistance of a single switch contact seems to be between 10 and 20 milliohm. Depending strongly on age and wiper downwards pressure. Better than most signal relays, but not exactly spectacular. Okay, so nanovolts are probably only of interest to 1 in a million or 1 in 10 million people. But on the off chance that one of those rare specimens is watching, here are the aforementioned footnotes. Generally, I don't think this is reliable enough for the general public just yet.
Oh no, not again.
I'll push what I have on GitHub for experimentation, but I wouldn't recommend building one until it says so in the README. It's mostly the homing that is making things difficult. Here's the latest idea that is also, you guessed it, not satisfactory. This would work great, of course, but those motors are pretty expensive. And you really also have to nail the 3D print. ASA is not an effortless material to master. Here, for example, I've specifically painted the seam to never be on the wear surface, but there is still something bad happening. Turns out the cross-section of that wiper part is just too small. Too many corners, retractions, and jumps in too little volume caused the extruder to stay there for too long and to overheat the whole thing. I've added an inconsequential hammerhead to that part, and that made it better. Still not perfect. The slightly squished first layer is causing higher pressure on subsequent layers, and therefore a slight bulge. Even such a near imperceptible flaw is immediately punished by uneven wear in the copper. There is also an inherent risk built into this kind of rotary switch conglomerate. The risk of a drive-by shorting, as in we are putting signals on these internal multinodes, and then in subsequent configuration steps we might short them out, or even 69 2-voltage standards, simply because we may have to touch many switch positions to get to our safe destination. It would be an interesting algorithm programming challenge to see if we can navigate to all states, guaranteed without accidents. But maybe not for me. That would delay this long overdue release by another month or so. I think I'll apply a bit more polish and then I'll present the final result in an also overdue nanovolt meter video. Is anybody old enough to remember when car ignition distributors worked like this? Hey, maybe there's our future nanovolt switch technology. Steering wheels also often have cool high reliability slip rings. Oh well, thank you for watching. See you next time.